Hello friends, in this video we will try to redesign the reverse curve ahead of the bridge number 40 up in Lucknow Kanpur section. So let me just briefly show you the data that we have. So this region is the bridge 40 and 40A2 and track up. This is the last channel sleeper data of this 40 upline, and this is the first channel sleeper data, this track up of the bridge 40 up. Then there is a straight portion of approximately 190 meters from here to here. Then there is bridge 39. Bridge 39 is bridge 39 is from here, from this location to somewhere around here. Our concern in this video is about bridge 40. So bridge 40 starts from here, ends here, and then as you can see, this is the upline like this, and this is the downline. So our concern here is the upline. So let us first draw the approach tangent which is outside the transition length. We select the line point and join these two by straight line. So this is our terminal tangent. Basically it joins two ends of the bridge, and this level that we have here, the point that we have here, is basically inner edge of left rail head. As we can see in the presentation, this point, this is the rail head, and this is the inner edge of rail head top, and this point, and we have chosen the left rail. So left rail head inner edge, running face or gauge face. Now there are some errors in nomenclature at some places, but mostly it is correct. So this is curve 21.0 right side of rail, and this is curve 21.0 station number 0, and TTP1, that is station number 0. Okay, curve 21 station number 0, which is TTP1. Two readings have been taken here, so we will use either of them. They are almost at the same location. So what we will see at the first, what we should first check is whether our TTP1 is correctly aligned with respect to our terminal tangent. So this is our terminal tangent. We will extend it. Let's extend it up till far end. Let's extend it up till here. Select this, then we go to extend, and then we select this. So this first terminal tangent has been extended along the track, and we see here that and this is increasing direction. Okay, so Kanpur is along this direction, and Lucknow is along this direction. So this is the increasing kilometer, and let us see how far is the TTP1. TTP1 is at a distance of, from last channel sleeper, 17.733 meter from the last channel sleeper. And this data we can also ascertain from some previous inspection that we have. Let us see on this side, curve 21 and then bridge number 40 up, and it was between this. So we have not written distances here, but it was approximately 17.7 meter, which is also coming here also. And this is C21P1, actually it is -1 station. So let us correct it. it's M1, M1 left side, and this is M2 right side, M1 right side. Alright, and so this would be approximately at 10 meter behind, minus 1 station. So this is 9.895, approximately 10 meters. So the first thing that we need to see whether our TTP1 is properly aligned or on the same alignment as our bridge proper. So as you can see, we had shown in the presentation also that let me open the photo of bridge 40. This is 39 and then we have this 40. See, this is A2 of bridge 40 up, this is A1 of bridge 40 up, and this is TTP1 of curve 20. As you can see, this is the increasing kilometer, and the TTP1 and other stations on the curve like station number 1, 2, 3, they seem to be out of alignment, or rather they have bulged. The track has shifted outwards. In this view we can say shifted towards right, but if with respect to increasing kilometer, like if somebody is standing here and looking towards this direction, so this track has shifted left side, and that is seen in AutoCAD file also here. Like this is A1 of bridge, abutment A1, this is abutment A2 of bridge here, and this is our TTP1 of the curve 21, and this point is left side of this line. So how far is this? So we can see it is like 0.4, 40 mm. We have 2 points here, so we have selected this one as the correct one for the time being. So 40 mm out of line, and this was a data. This data that you see here, CNB side, this one. So TTP1 was 26 mm. Here we are getting 26 mm. TTP1 was out of alignment, slew to left. So we needed it to slew towards left. Just a minute. Slew to right. Slew 26 mm. Slew to right was needed. And here we see it is 40 mm. What is the difference? Difference is actually this survey was done later. This survey was done later than this data, and the 26 value that you see is with respect to created. So this first survey is not visible. Let me ascertain. The survey was done on 17th of 024. Alright, this is the correct one. VFX file. Properties. 24th February 2024, and this one was another survey. Basically they are data of two different surveys, so it is differing. Let me open it also. This is the one. This survey I had done myself, so I had not lifted all points on the data. Only some of the points I had lifted, and this is this 39, and this is 39. So here it is, yeah. And then A1RR. So I had lifted very few points. This is A1RR. Repeat, RR means repeat. This is -1, and somewhere here is A2RR. Font has been reduced actually. I should increase the font size. Let me try to increase the font size. So we joined this line, these two, A1 and A2, and this is M1 has an error of 15 mm, and here if we see TTP1, that has error of 26 mm, as you can see 26 mm. So this data, 26 mm that you see and 15 mm that you see, this much slewing is required to correct the alignment, and this I have already explained in the PPT. Case 2 increases just outside transition of curve, example 3, base 40 up. So this goes like that, and until here is the explanation, and we have used only, and this analysis is correct only for first stage of tamping, and for second, third, fourth stage of tamping we will have to resurvey actually, because there is the change station to station change in slewing is too large here. That 0 to 41, this is too large slew, not acceptable. 0 to 43, at station number 2 you slew 0, and station number 3 you slew by 43 mm, which is too large. So these three are not acceptable actually, but the first stage of slewing is acceptable, 15, 26 and likewise. So in this analysis we had used the formulas for till TTP1, in fact till CTP1 we had seen what is the offset of the point from terminal tangent. Here it is, like for CTP2 we had, CTP2 is here, station number 3, and it was 079. So it was 079, station number 3. CTP is station number 4 actually, 0, 1, 2, 3. 1, 2, 3, 4, 1, 2, 3, 4. So station number 4. Just a minute, let me cross check. Actually this CTP1 is 40 or 30 meter. The transition length is 30 meter or 40 meter. Let me cross check it. Here it is. So station number 1, 2, 3, TTP1 and CTP1, 1, 2, 3, 4, 40 meter. 40 meter is the length of transition. So we will go till station number 4 actually. This is station number 4. This is station number 4, and this is the terminal tangent, and what is the offset here, and we see here it is 47 mm. So station number 4, that is CTP1, is 47 mm left side or outside the terminal tangent, when in fact it should have been an value of 152 mm right side of the terminal tangent, where 152 value we get by this formula. The y coordinate of cubic transition formula, we get one value 152. When we put the values here, this 152, as you can see, the formula is y equal to x power 3 or x cube upon 6 RL. R is 180 for 1 degree 1750. Total length of transition portion is 40 meters, and x is also 40. So when we put x equal to 40, r equal to 1750 and L equal to 40, we get the value of y is equal to 152 mm here. It is in meters, so this becomes 152 millimeters, and that should be 152 millimeter inside the curve, inside the terminal transition, terminal tangent. But actually it is 47 mm outside the terminal tangent. So overall slew that is required at station number 4 according to this data is 147 plus 152 mm, which is basically slew required slew to right, which is nearing 199 mm actually. So approximately 20 centimeter of slew is required to correct the alignment of CTP1, that is station number 4 of the curve number 21, which is approximately 40. This is 40 meter and this is 17 meter away from this 40 up. So this was data that I had surveyed, and I had taken only I had lifted only few stations of the approach in total station. So there was another survey that we had repeated again, where we had taken all stations, like see curve 21 station number 16, curve 21 station number 18, which is basically TTP2 CTP2 actually, and then curve 21 it's 21 only, and TTP2. This is left side of rail actually. Let me correct it. Curve 21, station 21, and then this is TTP2, and this is left rail actually, so left, and this is right. So fine. So we have and this nomenclature is incorrect actually. This is not TTP2, TTP2 plus 1, TTP2 के आगे एक station. So instead of this we can simply write it plus 1, curve 21 underscore plus 1, and this is R, and curve 21, because ahead of TTP2 हमारा plus में station आता है, TTP2 लिखने की दोबारा जरूरत नहीं है, plus 1, and then curve number 22 starts here, TTP2 plus 1 R plus 1 R, and this is curve number 2. Station 1, this is the actual TTP1 of curve number 22. See, it is written as curve number 22, station number 0 actually. Station number 0, this is TTP1, and this is the right side of the rail, and this is curve number 22, station number 0, which is TTP1 and left side of the rail, and this is actually not P1, this is -1 actually, so we will correct it as M1 underscore L, and this is also M1 underscore R. Alright, so this is curve 22 TTP1R, curve 22 TTP1L. Now this is actually plus 1, it is not plus 1, it is actually station number 1. So everywhere it has used P1, P2, but it is actually station number 1, station number 2. Likewise, it goes out to station number 9, station number 12, station number 15, 16, 17, 18, 19, 20, and this is the 21. So this is 21, this is the TTP2 actually. So curve number 22 underscore station number 21 underscore, this is TTP2 underscore R, and this one is, we have two readings here, so we will use one of them. Alright, so this is curve number 22, station number 21, and TTP2 underscore left side of the rail. Alright, so basically we have a reverse curve, and what was observed in earlier data that we have already seen in the presentation is that outside the reverse curve, CNB side, Kanpur side also, the CTP2, which was the station number 17 of the curve number 22, there was an error of 152 plus 19, which is approximately 160 to 170 to 171 mm of error is found in this. So basically what had happened was that, as per previous data, and the same will be found in this data also, that this terminal tangent that we had, 16, 17, 18, 19, TTP2. So this is TTP2 here. Our reverse curve ends here, and then it is supposed to be straight. But what we saw that in case we had drawn a straight line, this is the one we have here, 39, this is curve 20, this is also 39, curve 20, and this is here, yeah. So station number plus 43 plus 42, station number 42 as a matter of fact, it's not with respect to plus, ahead of the TTP2, then station number 22. So this is TTP2, this is station number 22, which is basically plus one station, and same case here also, the TTP2 that we had, this one. So when we draw a long alignment, let's assuming station number 43 as good point, and there were two options for drawing terminal tangent. CNB side of the reverse curve was selecting this point, the furthest most point as good point, and drawing a line parallel to the first terminal tangent. So, or another option was we could select 2 points outside the reverse curve, like which are quite far, like station number 43, and we may select like station number 37 as good points, draw a straight line, then extend it towards the reverse curve, and then see what is the offset. Whatever we use as the terminal tangent, we saw that just like at start of the reverse curve, the track has bulged outwards. Same was the case other side of the reverse curve also. There also, the curve has bulged outside. So here we needed a slewing towards this side, which means towards right if we are looking towards the upside with respect to increasing kilometer, and another side the slew was slew towards left. This is our curve is ending here, but we need to slew the track towards left to make it a proper reverse curve. So this data, this calculation we had done using y ordinate of transition cubic. Alright, and that is what we will show here. That is what we had shown. We have already shown the calculations and fundamentals here in the previous slide. Next slide that we are going to create is basically taking into consideration full reverse curve. What we had done earlier in earlier example is we had only taken the transition portion of the reverse curves end side. So what we will try to do is we will try to redesign the whole curve. For the time being, we will assume that there is no restriction to amount of slewing that we can do. However, practically that may not be the case because we have OHEs locations and and there is a critical distance. The distance of OHE mast from track center should not be less than certain parameters, which could be 2.8 meter or which could be 3 meters. So leaving aside, let us first try to draw a reverse curve which starts here, that is to say TTP1, the start is same and then ending is also same, and let us for the time being assume that the initial terminal tangent and the final terminal tangent have are parallel to each other as a matter of fact, which may not be the actual case. So in this case we will draw a line parallel to this terminal tangent and use a point on up line, like this is the track up. So we will use this point, the furthest most point, and let us see how far it is from this line. So we see it is 23.42 0.23 meters. So we will copy this line, copy selection. So this point we will move here. Alright. So just like that, we draw the terminal tangent CMB side of the reverse curve, and let us see where is the TTP2. TTP2 would be somewhere here, 14, and this is TTP2, and we see that there is not much error according to this. So let us take it, let us use this as the correct point, for example, and we see the error is 87 mm. But yes, 87 mm is the error in TTP2. Likewise, we can find this is +1, the error is 54 mm, +2, error is 25 mm, +3, error is much small, 11 mm, +4, error is 10 mm, +5. Now error has reversed actually. In this case, we need to sleeve the track 4 mm to right side. This was +6 actually. It is almost on the almost 0 actually. Then +7, 39 mm to right. So likewise, we can find all these points, and up till +10 and +11, up to +11 ahead of the TTP2, we have 11 stations ahead of TTP2. After that, the data has been taken at approximately 30 to 40 meters distance, like this data here. Alright, so how do we proceed to draw the actual reverse curve? Our TTP2 is here. TTP2 is here and it ends here basically. So we have to draw a reverse curve between this point and somewhere here. And the parameters of the curves are total length of the curve, first circular curve. First curve is 21 stations, that is 210 meters. Second part of the curve is also 210 meters. And there is a middle straight portion which is approximately 55 meters. So basically from TTP2 of curve number 21 to TTP1 of curve number 22, this distance is 57.168 meters, approximately 57 meters. Alright, so how do we proceed to draw the ideal curve? By the way, this data that we have used, we are using the left rail. We are using the left rail for analysis. Right rail data we have not used. And so first we begin by we will not change the start and ending of the reverse curves. So basically let us draw a line. For example, first let us draw a line, or rather we need to draw a perpendicular line from this. So what we can do is copy selection, and then we will copy selection and we will this select this and then move it to TTP1 of the curve. Let's see here. Then what we will do is we will trim this line Alright, delete this also. Then we will rotate this line by 90 degrees. Rotate 90. Alright, so basically this is our start of the reverse curve. Let us give it another color, let's say green, and again let's copy it, copy selection, and this point we will take it to CTP2 of the curve number 22. Just to revise, basically we have curve number 21 and curve number 22 which constitute the reverse curve. Alright. Move. Okay. So here's at TTP2 we have 2 points actually. To know which is the correct one, let us do one thing. Let us see what is the average, but this distance is not actually okay. Let us see what is the average distance between two left and right points. Like here it is 1.693, here it is 1.69, then here it is 1.695. so basically 1.693 is the average. So which of the 2 points should we use? Like this is the one, here we get 1.669, and second one, if we choose this one as the correct point, we get 1.702. so second one is the incorrect one, so we will delete it and we will use the first one as the correct. So we will move this line from here to here. This calculation is with respect to second, so this is also correct, and for the time being we will change its color to little bit invisible. This we need to change the color. It's not, let us change this. We need to change the color of this. Control 1 color. It's not accepting actually. Or we can delete it. Let's delete it. Alright. Alright. So this, we draw reverse curve from this to this. Alright. And this line is the first terminal tangent, this line is the second terminal tangent, this is the TTP2 of curve number 22, this is TTP1 of curve number 21. Alright, so curve number 21 TTP1, curve number 22 TTP2, middle straight portion of 57 meters, each curve has length of 210 meters, that is 21 stations each. We see that the curve is not properly aligned. For reference, we also have observed versine data. Like this is 0, that is TTP1 of the curve number 21. Here versine is 4, 3, 14, 21, 35, like that. Then there is middle straight portion also. Here this is middle straight portion. Then we start with TTP1 of curve number 22. This is TTP1 of curve number 22, curve number 22 again. So here So just for reference, we also have the actual versine data, and as you can see, against the ideal value of 28.5 or 29, we have some places we have more, 33, 34, 31, 30. So basically the curvature is more, and that is the reason, like 31, 32 and then 32, and that is the reason for bulging of the curve. Either way, our purpose here is to redesign the curve ideally, and then we will see what is the offset, that is what is the swing that is required. Then we will also take into reference the OHE distances. Alright, so how do we proceed to design the curve? So for designing a simple curve, let me first give you an example. Like let's say I have one straight line like this, and there's another straight line like something like this. All right, exactly not matching, but something like this. All right, so I have two straight lines and I have to draw a curve between these two lines. So we use a function, we use a plugin. We will load this plugin by function by command appload, and then we will go to the plugin, that is auto LISP application, Lisp application. fspi is loaded. Okay, so now we will run the command fspi. We have to select the first tangent, so we selected this tangent. We have to select the second tangent, we selected this tangent. Curve radii, let's say we draw for 1 degree curve, so which is 1750 meter. Let's have transition length of, let's say, 60 meter. Second transition length is also 60 meters, and see, can you see, this has drawn the curve. This is the circular portion, this is the transition portion, this is also transition portion. Alright, and we have drawn a curve of which, if we measure the length of transition, we will get 59.999, that is 60 meters, as we has entered the value. Here again we will get 60 meters, and the arc length is not in our control actually. This is 140.988, which is basically 141 meters. So this is a command which we will use here to draw the curve, and what we control is the radius of curvature of the circular portion, and what we also control is the length of the transition length, but we don't control the length of the circular portion. That is automatically generated in the software. Alright, so to draw a circular curve, we need the terminal tangents, and we can use this fspi function command, fspi function, to draw the curve. Alright, but in this case we have to draw a reverse curve. Now let me first delete it. Here we have to draw a reverse curve from here to here. From here, this is the first terminal tangent up till here, and this is the second terminal tangent. We have to draw the reverse curve actually, and the middle portion has to be approximately 55 meters of straight line. So what we don't know is the terminal tangent for the first circular curve. First curve will start here, end somewhere here, and then there will be terminal tangent, but we don't know what is the terminal tangent orientation. To draw that, we will use a trick, and which is the basic. This is a reverse curve in which individual curves are having same parameters, like 210 meters length and 1 degree, and this also 210 meters of total length and 1 degree. So the terminal tangent will, the center of the middle part of the tangent or middle straight portion will be exactly in the middle of the this length. So what we will do, we will draw, rather what we will do is we will trim here. Alright, we have trimmed it, and we can trim here also, or we can draw another line. We have to measure total distance actually. So what we do, we have to measure the total distance from here. We need a point, this one. This is our ideal point actually. So let us draw a line first. This is, and let us delete this, and then let us draw another line by green color from here till here. This is the center. Alright, so again we will select the center and draw a perpendicular drop on the second terminal tangent. Alright, again, so this is the, so now we have got the central point of the reverse curve, and the middle straight portion will be something like this. Alright, and ideally the middle straight portion, the middle of the middle straight portion should be somewhere here. Alright, now, but what will be the inclination of the straight portion? So we know that the first part of the curve will be from here to here, second part of the curve will be from here to here. This includes the middle straight portion actually, and we also know that the middle straight portion will pass through this point. Right, another thing, like we have, so what we do next is we need this to select the orientation, and for that what we will do is, since the total length of the curve is 210 meters, and that is along the curve actually, not a straight length, either way, so we will go to the center of the track. What we will do, we will draw another line. We will draw another line, and which will be from CTP2 or we already have the data for C20. See, if we keep adding the respective distances from here, like this is station number 0, this is station number 1, this is station number 2. If you keep adding these distances, we already have a file for that. Let me open that file. So this is this curve 21, and TTP2 is at a distance of 227,925 millimeter ahead of the bridge, and if TTP is this, so total distance of this is equal to this minus this, 21.019 meters, which is 21 meter and 19 millimeter, or approximately 2 centimeters extra, which is almost 21 meters. So, and this is along the curve. What we can do is we can assume that the location of the TTP2 of the curve is correct here, and then we drop a perpendicular from this to the first terminal tangent, and then we draw another line from here till the first terminal tangent of TTP1. Now we got the central portion. So this point represents the center of the first circular curve, which will be between station number 10 and station number 11, which is also correct because that is what will happen. And similarly, we assume that this TTP1 of curve 22 is at correct location, and we draw the perpendicular here, then we draw a line from here till here, and this represents the total length of second part of the curve, that is curve 22. Now if we join this point, which is the center of this line, this here, and for this we have here, center is here, now if we join these two lines, these 2 points, that should ideally represent our orientation for middle straight portion, and which almost falling on this, the center of this line, almost falling. It is not exactly falling because these distances, or rather the points that we have selected for surveying, may not be exactly on the TTP2, maybe 5-10 centimeters left or right, but overall we can see that it is more or less correct. The distance is only 8 millimeters, so we can ignore this, and we can use this line as the terminal tangent for the curves. So what we get is basically we have this one tangent, then we have this second tangent, and then we have this third tangent. Alright, so this and this, between this we will draw a curve, and then between this tangent and this tangent we will draw another curve. Right. So let's delete this line, or let's move it upwards. Let's delete it. Let's move this also outside. Already we have this section here for our reference. We will not delete this line because it represents this line is being used to represent this point actually. Now we can proceed to draw the curves one by one. So first what we will do is select all these 3 tangents, and then press Ctrl 1, which goes to properties, and change the Z values to 0, 0 in each case, because the upload function fspi that we are using will not give a result if the 2 lines are not in same plane. So now let us proceed. We have first tangent, second tangent, or rather first tangent and second tangent. What we will also do is we will trim it from here. Alright, now let us draw the curve. So we will use fspi function, then we will use the first tangent, then we will use the second tangent, Now ideally it should satisfy the criteria of 1750 radii. Transition length was actually 40 and 40, so we will use same, and this is the result. So what we get here is our curve is starting from here. As you can see, this length is of course 40 meters as we have already entered, and this length is arc length is 113.3 meters, approximately 115 meter we can take, and 115 plus 40 plus 40, that is 80, so basically 195 meters against 210 meters. So the length that we are getting is less than what we should have got. Our curve should have started not from here as it is presently showing, but let us proceed with this for the time being, because on-site TTP1 is here, and what we have redrawn, the TTP2 is here, approximately 7-8 meters ahead. Approximately 7-8 meters. So 8 plus 8, 16. Our curve is 16 meters, 15 to 16 meters shorter than required. Before we make any changes, let us draw the reverse curve, the curve for the second part, for which we have this as the terminal tangent and this as the terminal tangent. First, before we do, we will trim it here at the intersection. Alright, so this is first, this is second tangent. We will load the command fspi. This is the first tangent we have selected, this is the second tangent. We had already ensured that the levels are, Z levels are 0 for both. We will select 1750 as the radii and 40 and 40 as the length. And now we have drawn this curve. Again, let us see what is happening here. Here also our curve is little shorter. It was supposed to, this is the second part of transition, it was supposed to end here, as you can see TTP2 of the curve number 22, but it has ended a little earlier, and that little earlier is this distance 8.02. 8 plus 8, 16. This gap 8.02 that we see here will also be reflected, like this is the second part of transition, this is the first transition. So this 8 will be reflected here also, because TTP1 was supposed to start here, but TTP1 has actually started here. This will also come approximately 8 meters only. Alright, 8.4, approximately 8. We can, for the purpose of our work, use this data as the actual or correct data, and every offset that we get here like this will give us the desired slew value. Like here we get 123 mm. We need to slew the track to right side, and this side, which is going away from the OHE masts, which is acceptable as a matter of fact. So we can draw, we can see here also away, here also away. Everywhere it is going away from the present position. The required slew is away. Right here also, let us see how much this value is. 123 here also. This is the transition portion. Again here also the new curve is away from the present position, and this is going right side, so away from the OHEs. This is the middle straight portion. The length of new middle straight portion has increased. Earlier it was 57 meters. Now it will be 74 meters. And let us see in this case here, it is the track is going towards the OHE mast like 111 mm. Here 65 mm, likewise here it is much smaller, only 43 mm. So you see what we did, we have this terminal tangent, this middle straight portion, and this the first terminal tangent. We have these three tangents, and we have the curves and overall reverse curve properly aligned, having degree of curvature 1, that is radius of curvature 1750 meters, and transition length is 40 meters in each case. We have redrawn the whole reverse curve using the correct alignment, and we can find the offset, the slew required at every location, and we can treat it as a final solution. What we will do, what we will need to analyze is whether or not we should use it as the right solution, or whether we increase the value of transition length by 10 meters each, so that our TTP1 and TTP2 come almost at the same location. So for that, what we will do, let us copy this whole file and copy selection, and let us move it here, and then so basically we already have a solution, and we will get the offset, or not offset but rather slewing required at every station, the station number of the curves, and then we can compare the changes in distances from OHE. What was the OHE distances before, and what are the OHE distances after the desired slewing is effected, and whether it is acceptable or not, whether it is coming more than 2.8 meter or not. We can try another solution. So let us try another solution, because we saw that the overall length of the curve was less than 210 meters. It was approximately 195 meters in both cases. And so it is copying actually. Yeah. So earlier solution we had used only tilted CTP2. We have seen offset at CTP2 both ends of the reverse curve, CTP1 of the first curve and CTP2 of the second curve. We had designed the curve using y-ordinate of transition formula. This is the y-ordinate value that we had got, 0 to 19, 64 and 152, and this was also, we also saw what is the offset, what is the swing required with respect to terminal tangents. So counting in both, we got what is the required slew overall till CTP2, and the slew at CTP2 whatever we had was then progressively decreased till the straight portion, till we got to middle straight portion. So this value 50 at station number 17 was decreased to 0 at station number 1, that is 170 meter behind, gradually reduced. Likewise here also this value 50 was gradually, we used 50 as the maximum slew that a tamping machine can effect is only 50 millimeters. Although overall slew required here was 199 millimeters and overall slew required here was 171 millimeters, but for first round of tamping we will go only up to 50. So this was the one way to solve the problem, where we took into consideration only the transition portion and we used the y-ordinate formula, that is this formula, y equal to x 4.6 r. And what we have done now is we have drawn the whole curve, whole reverse curve again. So this we can say is more perfect solution. However, we saw that the overall length of the curve in both cases was approximately 195 meters against 210 meters. So if you want to increase the length of the overall curve, we should increase the length of transition. So we can try with, in this case, let us try with using transition length of 50 meters. So we will delete these. We will not delete the middle straight portion, and we will delete the curve. Alright, so we will again extend the lines. This was our first tangent. In fact, this was our first tangent, this was our second tangent, middle portion of tangent, and this was our third tangent. We will extend this line from here to here where it was going. Alright, and we will extend this line which has started from middle portion of the second curve, which was here. We will also extend its another. Basically we are redrawing the tangents, actually nothing else. We are redrawing the two tangents. Alright, so and then we will trim it, the extra part we will trim it. This side also, whatever is extra we will trim it. Alright, so we again have this first tangent, the second tangent, and then third tangent, and we had already, okay, we will make the values of Z00 again here, in this case also. Alright, and then we will again draw the curve. Alright, this is mistake here, this line will not go here, it will go in fact here. Alright, alright, almost here. Okay, and we will have to extend this line from here till here. So now we have three tangents, 1, 2 and 3, and Z values are made 0 for all the three lines. Okay, now we will run the fspi command, the app. We select the first tangent, we select the second tangent, the curve radii is 750 only, and this time we will use the transition length of 50 and 50. Alright, so what we see is that in this case the TTP1 has moved by 3.22 meters instead of 8.22 meters earlier, which is almost near the present TTP2. So we will accept it as the correct solution. We may also use, instead of 50, we may try with 60 meters. Let us see. We are increasing the transition length because the higher the length of transition, the more smooth will be the curve. And using this, we can also experiment, or we can analyze whether speed relaxation is possible in this curve without any changes in the position of OHE mass. So we can go for, let us control Z. Alright, let us again try. We will again run the fspi command. We will select the first transition, second transition, curve radii 1750, enter, transition length we will use 60 and 60, and here we go. So this case our curve is starting a little earlier than TTP, like 3-4 meters, 1.78 meters. Alright, 1.7. So we may accept this as the new solution, alright, which is 1.78 meters this side. So it will have gone approximately 1.78 meters this side also. Okay, somewhere around here, 1.382. So overall length of middle straight portion is going to decrease. Alright, so we have used 60 meters and 60 meters as the new transition length. Now let us also draw for the second portion. We will again use command fspi. We will select first tangent, then select second tangent. Curve radius 1750. We enter it and we will use 60 and 60 as the length. So what we see earlier, TTP1 of curve 22 was here. Now it is slightly behind it. Here, 1.579. So length of overall curve has increased by 1.579 one side, and another side also it has increased a little. Earlier TTP2 was here, now it is here. So this is also approximately 1.97. Okay, and overall length of the middle straight portion should not be less than 50. So what is new length in this case? We see it will be more than 50. As we can see, it is 54.207. So new transition length we have used is 60 meters. 59.999, that is 60 meters. Length of curvature is not in our control, it varies as per the software's analysis. It is 93 meter in this case. Again, the first transition length is also 60 meter in this case. So you see, we have again redrawn, like first time we had drawn using the same parameters as was available in our TMS, that is the 40 meter is the length of transition both sides, and overall length of the curve was 210 meters. When we used to draw, we found that the overall length of the curve was 195 meter against 210 meters. And when we used the transition length as 60 meters, overall length of the curve was approximately 3 to 3.5 meters more than 210 meters, that is, we can say 213 or 214 meters. The advantage we have is that our length of transition has increased to 60 meters. Also, for the purpose of speed relaxation, we need higher length of transition, and that is what we are getting here. So this solution is more desirable provided our OHE parameters are more correct. So what I will do, I will pause the recording for a time. I will calculate the required slew when the transition length has been used as 40 meters, in which the overall length of the curve is 195 meter in each case, and second when the length of transition is 60 meters, in which case the overall length of the middle straight portion is 54.207 meters. I will also, and what is the required slew at every station, and I will also use a third criteria where I will use the transition length as 70 meters, because if we get the transition length as 70 meters, we can draw this reverse curve for sectional speed of 160 kmph against currently that we have for 110 kmph. So this is also important part of analysis. So I will pause this video and I will again restart after I have calculated all the required slews for the new curve that we have drawn for transition length 40 meter, transition length 60 meters, and then transition length 70 meters, and we will compare the OHE distances, and then we will see whether we can not just correct the the approach curve, but also redesign the curve in the same process to make it fit for 160 kmph.